Hello again, this is Al, and welcome to lesson 36 in this series that is beginning to look a lot more like something to do with maybe C++. Although we are dealing with C currently, and I have added a new project in our tests folder. Here's the tests. Here's one test, and in this test, I'm looking at the problem of dealing with a linked list. Now, I don't know if you know what a linked list is. The idea is quite simple. It's very simple, similar to the stack frame idea. If you recall, the stack frame. At certain points, at some point in memory, let's say, is an address which I'm going to call node with a number 1, let's say. So in our assembler language, that would be like that. Underneath this node 1, directly underneath, that really means at this address, is the address of another position in memory, a number representing another position in memory, node 2, along with some data. Okay. Now, somewhere along in memory is node 2. Has an address of another node and some data, and so on and so forth. Now, these nodes do not need to be in order in memory. Node 3 could be up here. Another label. And some data, and so on and so forth. Eventually, though, however, at some point when you get to the end, this one of them is going to have null for the next node and some data, but at this point it stops. When you hit the null, then you're done. So this would be a linked list containing 4 objects, 1, 2, 3, and 4, not aligned in memory, but nevertheless 4 nodes and the various data. Okay. Now, I made a separate file for managing the nodes as a function for adding a new node to the list at the end of the list, in fact, and for allocating a new node, not the data part, but just the node part. And in this header file is the definition of a node. First member is a pointer to the next node, and the second member is a pointer to the data. So the user of this node manager system that we're developing would supply their data in here, and it's up to them to free the data when in the nodes when the time comes and they're finished working with it. Okay. Now, in main here, I've defined here a pointer essentially to a node. So, well, I've defined unknown where this linked list, where the first node is, would be contained eventually in this value. This value will be equal to this, but we don't have that yet. Now I called this p-linked list because this is the head of the list, and from here you can get to all the other nodes. Now this is a what they call a unidirectional linked list. It only goes in one direction. Other types of linked lists have a pointer to the previous node as well as the next node, but this one only has the next. So the only way to traverse the entire list is to start at node 1. So therefore that has a unique quality to it. That is the only reference to the entire list. This thing references part of the list. I can see everything except for the first node, and so on. Each node on its own actually represents a sublist inside of this linked list. Okay, now how does this work? First, lacking data, I decided to use the passed-in arguments of the program as the data parts for the nodes. So we call node F11, by the way, can take you to definitions, and control the star on the numeric keypad will take you back. We allocate a node. What was I just about to explain? Oh yes, I'm using the passed-in argument. The way to pass arguments into your program is in the debugging menu and configuration properties command arguments, and I put one of those weirdo command lines that we've been working with as what I passed in, and that's going to give me a whole bunch of things to add to my list. You could imagine this seems totally useless since I already have a list containing all those strings, but you could imagine another linked list. So I could call this list args and list switches or something. I could have two of these, and that would be one way that I could separate arguments out from switches and deal with each independently if I wanted. So there's a possibility that this could be of some use. Okay. Now, well, I guess I might as well just start stepping through it. In the end, I'm going to print the list out this way. So maybe looking at this might help you understand the concept. If this here P node is the head of the list, this says while there is a node, print the data for that node, and then change P node to the next value of that node. And that's how you advance through a linked list. Okay. Now, you'll notice that stuff, yeah. Okay, well, let's first just go through the simple part first. Allocate a node. A node, you recall, is just 8 bytes, one pointer for the next node, and one pointer for the user's data. So that's 8 bytes. It allocates that much. Here it is. All CD, CD, CD. That means allocated memory. The next pointer is always set to 0 when you allocate. And on purpose, I leave the data part as CD, CD, CD in case you happen to run across this in the debugger. You'll know that that's allocated memory that hasn't been freed yet. So I'll leave that as it is. Okay. Now I'm going to take the argv of 0, which is the name of the program, and set that to the data part of our node. This currently has no next pointer, but now here's the data. It won't print out the string because this is of type p void. It is possible though to cast this as a car star in the watch window, so you can look at the data as if it were a car star. Now the bit about adding it to the list. Now recall this here, I want to point to the first node in the list. In fact, this is the first node in the list. Essentially, what I want this to do is assign to this guy this value. Now I could just do that, but I don't have to. This add node thing will always work correctly no matter where you start from. Initially, this is equal to null. Okay, and I'm sending the address of this here. Okay, now this here is a variable somewhere. Could be, oops. It's on the stack, it turns out. But it's somewhere off in no man's land. Okay? And it has a value of 0. I want that to be set equal to node 1. And so I'm passing the address of p-linked list into this function, and it should set this value equal to node 1. And you'll see that happen. Okay. Now, in general, I'm thinking of this as the head of the entire list, and I'm calling this next node because we might be advancing to further nodes as we move along. We're looking at this from a sort of pointer-centric point of view. That is, we're only concerned with p nodes, only concerned with these addresses. Okay. Now this says while the value at a given address is non-null, well, it's null, it's passed in null. A valid address, but null. While this is not null, do something. Well, in the first case, it is null, so it won't do anything here. So now it just sets the value of the thing I just passed in, which was the address of this thing. It's going to set that equal to node 1. So here you can see our list has one entry in it. The only entry in it has the next value of null. And as you'll see, if I add another one, I just allocated another new node. Okay, and I'm setting the data, in this case the word this, and that. Now if I go into add node, again, this thing is still pointing here, but this now says node 1. Okay, okay. So the star of that, where are we now? We're in here. Let me just first set this. The star of P next node is not null. The star of that is equal to node 1. And node 1 could, in theory, point to another node. So we check. Is the star of the node passed in null? Not null. Now I would like to extract the address where the next pointer for that node is stored. That is, where is the address of node 1's next node? That's the address of this piece of memory. And that, in fact, contains null at the moment. So now we advance, and we're going to check and see that that, in fact, is null. So now, this thing here, this pointer is going to be set, whatever is at this address is going to be set equal to the value of the thing that we just passed in. P node, the next node. Now I got that number right. So we got node 1, which points here, and now we've retrieved the address of this spot, which will be filled in with the new node which is passed in, node 2. And so now node 2's value will go in here, which is what we want. So that's done. If you look at our linked list now, we have 2 items, and so on as we continue along. Eventually, we'll get the last one. Now we're done. Now here's our, in total, our list contains all these elements, and that's the last one, no more next. So what is that? Six elements, same as argc. Now I'm going to go print them out, and I'm starting from the head, linked list. While P node, which is the head, certainly not null, I'm going to print his data as if it were a car star. There it is here. Okay. And I can also put in here the next. Okay, we printed that. We print that out. Now to advance to the next, we go to P nodes next. This one. So now, see, P node is data has become the word this. We print it out. This. Advance to the next. Print it out. Is. And so on 6 times. Now the next of this one is going to be null. So this node's next is null. And we're done with the printing. And this extra bit is, I had to add because for some reason with the weirdo command lines it doesn't pause properly at the end. Alright, so why am I looking at this? Well, the interest here is in this node manager, uh, this linked list node manager unit or whatever, this list of functions that we can build to manage adding and removing and inserting nodes to and from these lists. In fact, adding to the head of the list is a one-step operation. You don't have to walk all the way to the end. We can insert at the head of the list immediately by simply taking the passed-in value and pointing it to the current first node, which might be null, and so on. This is an example of a collection of code functions that operates on data, that operates on data related to these functions in a particular way. And it's an example where, in a sense, C fails us in one of our goals, which is the tighter binding of code and data. We'll have a collection, I'll finish this, and we'll have a collection of functions for managing these nodes and these lists, adding, deleting, etc., and so on. But the two here, the node and the functionality, will always be separated. They're not bound in any way. I can, although it's good that in general I can use this functionality for nodes and lists of any type of object with the same functions, we have to omit the type of data we're dealing with, so we can't really check to see if we're maybe we're being passed one node with strings and another node with another type of data that's mismatched. And because of that loose binding between this code and data, the code is more prone to error than it would have to be if we could somehow manage to connect the functions with the data in a more natural and easy way. So this is a good example of where C++ excels in doing something like this. So I'd like to go through adding all the functions and then maybe show you how it's done in C++, or take a different example. I'm not sure. Okay, so I'll leave that there. Okay, see you next time.